welcome to this problem walkthrough. Today, we'll be exploring problem number 1177, can make palindrome from substring. This is an interesting problem that challenges our understanding of string manipulation and optimization techniques. Let's dive in and break it down step by step. In this problem, we are given a string S, and we need to determine if specific substrings within S can be transformed into palindromes. A palindrome is a sequence that reads the same backward as forward. To achieve this, we are allowed to replace at most k characters in the substring. Each query in the input specifies a substring via its inclusive range, left, right, and also provides the value of k, which limits the number of character replacements we can make. The task is to evaluate each query and decide whether the specified substring can be made into a palindrome with the allowed replacements. This problem challenges us to efficiently handle multiple queries while working with large inputs, as the string S can be very long, up to 100,000 characters, and the number of queries can reach 10,000. The output for this problem is a list of Boolean values, where each value corresponds to one of the queries. For each query, the result is true if the specified substring can be converted into a palindrome using at most k replacements, otherwise, the result is false. Let's look at some examples to illustrate this. In the first example, the input string is S equals ABCDA and the queries are 3, 3, 0, 1, 2, 0, 0, 3, 1, 0, 3, 2. For the first query, the substring is D, which is a single character. Since a single character is always a palindrome, the result is true. For the second query, the substring is BC. This cannot be turned into a palindrome without replacements, and since k equals 0, no changes are allowed, so the result is false. In the same example, let's analyze the remaining queries. For the third query, the substring is ABCD, and we are allowed up to one replacement. To make this substring a palindrome, we would need to replace at least two characters, for example, changing B to C and D to A. Since k equals 1, which is less than the required number of replacements, the result is false. In the fourth query, the substring is again ABCD, but this time k equals 2, meaning we are allowed up to 2 replacements. This is sufficient to turn the substring into a palindrome, so the result is true. Another example involves the string S equals AAA in queries like 0, 4, 0, 1, 3, 1, 0, 2, 0. In this case, all substrings are already palindromes, so the result for each query is true, regardless of the value of k. Finally, let's consider the constraints in some edge cases. The string S can have a length of up to 100,000 characters, and there can be as many as 10,000 queries, so efficiency is key. Each query specifies a valid substring range, left, right, and a non-negative k value that does not exceed the length of the string. Edge cases to keep in mind include single-character substrings, as they are always palindromes, and scenarios where k is large enough to allow any substring to be transformed into a palindrome. For instance, if k is greater than or equal to half the length of the substring, we can always make it a palindrome. Another edge case is when the substring is already a palindrome. In such cases, the result is true regardless of k. Performance considerations must be addressed to handle the maximum input sizes efficiently. To start, let's consider the brute force approach to solving this problem. The idea here is straightforward. For each query, we extract the relevant substring, calculate the frequency of each character in that substring, and count how many of those characters have odd frequencies. This is important because a palindrome can have at most one odd frequency character in the case of odd-length strings, or none at all for even-length strings. Once we have the odd frequencies, we determine if it's possible to convert the substring into a palindrome by replacing at most k characters. For example, if two characters have odd frequencies, we would need at least one replacement to fix both of them, and so on. However, this approach becomes computationally expensive because extracting substrings and recalculating frequencies for each query both take linear time. If we have a large number of queries or a long string, this quickly adds up to an overall complexity of O(n*q), which is impractical for larger inputs. The brute force approach, while intuitive, has significant drawbacks. It involves repeatedly extracting substrings and recalculating frequencies for every query, which makes it inefficient for large inputs. When n or q reaches the scale of 10,000, the method becomes infeasible due to time constraints. To address this, we can use an optimized approach that avoids redundant calculations. The key insight here is to pre-compute cumulative character frequencies using a prefix frequency array. This allows us to calculate the frequency of any character in a substring in constant time. Specifically, the frequency of a character C in the substring can be derived by subtracting the cumulative frequency at the start of the substring from the cumulative frequency at the end. Using these frequencies, we can count how many characters have odd frequencies and check if the number of replacements needed to fix these odd frequencies is less than or equal to k. This eliminates the need to repeatedly count frequencies for each query and drastically improves efficiency. With the optimized approach, we achieve a significant performance boost. First, we pre-compute the prefix frequency array, which takes linear time with respect to the string length, specifically 26*n, since we track frequencies for all 26 letters. For each query, instead of recalculating frequencies from scratch, we simply use the prefix frequency array to determine the odd frequencies, which takes constant time for each character. This reduces the time complexity for processing all queries to O(q), resulting in an overall complexity of O(n plus q). This is a huge improvement over the brute force approach, especially for large inputs. However, this method does require extra space to store the prefix frequency array, which has a size of 26*n. Despite this, the trade-off is more than justified, as the time savings are substantial and the method scales well to handle large values of n and q. Ultimately, the optimized approach using prefix frequency arrays is the most efficient and practical solution for this problem. By pre-computing data, we eliminate redundant calculations and achieve a time complexity of O(n plus q), which allows us to handle inputs as large as 10,000 within time limits. This method is not only efficient but also scalable and relatively simple to implement, making it ideal for this problem. While alternatives like the brute force method are easier to conceptualize, they fall short of handling large constraints. On the other hand, more advanced techniques, such as bitwise masks, can provide marginal improvements but introduce unnecessary complexity. The prefix frequency approach strikes the right balance between simplicity, efficiency, and scalability, making it the clear choice for solving problem number 1177 effectively. To understand this problem, we need to determine if a substring from a given range can be turned into a palindrome by modifying at most k characters. A palindrome, as you know, reads the same forward and backward, so the order of characters plays a critical role. The challenge lies in optimizing this process for multiple queries efficiently. To achieve this, we pre-process the input string using a prefix frequency array. This array helps us track the cumulative frequency of each character at every index. By doing so, we can quickly compute character frequencies for any substring without recalculating them repeatedly, saving significant time during query handling. The pre-processing involves initializing a 2D array, where each row corresponds to a character in the alphabet. As we traverse the string, we update the cumulative frequency for the current character while maintaining the sums for all other characters. This setup ensures that our solution is not just correct but also highly efficient when dealing with multiple queries. Now that we have the prefix frequency array, we can efficiently process each query. For a query defined by the range L, R, and the allowed changes k, we calculate the frequency of each character in the substring S, L, R plus 1. Using the prefix array, this calculation is as simple as subtracting the cumulative frequency at L from that at R plus 1. Once we have the frequencies, we count how many characters have odd frequencies, as these disrupt a palindrome's symmetry. The key insight here is that a substring can be transformed into a palindrome if the number of odd frequency characters is less than or equal to 2*k plus 1. This is because each modification allows us to adjust one character, and at most one odd character can be left unpaired in the center for odd-length palindromes. After counting the odd frequencies, we check if this count exceeds 2*k plus 1. If it does, the substring cannot be rearranged into a palindrome within the allowed modifications. Otherwise, it can. Finally, we store the result of each query in a list and return the results after processing all queries. There are a few key insights that make this approach efficient. First, the prefix frequency array optimizes substring frequency calculations, reducing the time complexity from O(n) to O(1) for each query. This is crucial for handling multiple queries efficiently. Second, the odd frequency check is central to the problem. A palindrome can have at most one character with an odd frequency for odd-length strings, and none for even-length strings. Allowing k modifications means we can tolerate up to 2 k plus 1 odd frequencies, giving us a clear condition to evaluate. Third, there's a balance between pre-processing and query processing. The pre-processing step, which involves creating the prefix frequency array, takes linear time relative to the string length O(n). Query processing, thanks to the prefix array, is reduced to constant time per query, O(26), or just O(1), when considering the alphabet size as fixed. This results in an overall time complexity of O(n plus q), where q is the number of queries. Together, these optimizations ensure that the solution is both fast and scalable. It's important to address some edge cases to ensure the algorithm handles all scenarios correctly. First, if the string is empty, there are no substrings to process, so no queries should be executed. Second, single-character substrings are always palindromes since there's no symmetry to disrupt. Third, when the value of k is very large, it effectively allows any substring to be converted into a palindrome because we can make unlimited modifications. Finally, if no modifications are allowed, meaning k equals 0, we simply need to check if the substring is already a palindrome. Let's consider an example to illustrate this. Suppose the input string is s equals atba, and we have 3 queries, 0, 5, 1, 1, 4, 0, and 2, 3, 0. Each query will help us see how the algorithm evaluates different substrings under varying constraints. Let's walk through the example step by step. First, we pre-process the string atba to build the prefix frequency array. This array tracks the cumulative frequency of each character at every index. For the first query, 0, 5, 1, the substring is atba. The character frequencies are 2, 2, 2, meaning all characters have even frequencies. Since the odd count is 0, the substring is already a palindrome, so the result is true. For the second query, 1, 4, 0, the substring is bccb. Again, all character frequencies are even, with an odd count of 0. Since no modifications are allowed, and the substring is already a palindrome, the result is true. Lastly, for the query, 2, 3, 0, the substring is cc. Here too, the odd count is 0. So the substring is a palindrome without any modifications, resulting in true. The final output for all queries is true, 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 demonstrating how the algorithm efficiently determines the results. This solution efficiently handles the problem using a pre-processing step and prefix frequency arrays. Here's how it works. 1. Prefix frequency array. The algorithm first constructs a prefix frequency array prefix_frequency, where prefix_frequency, I, j, stores the cumulative count of the jth character, a to z, from the start of the string up to index I1. This pre-processing step ensures we can retrieve the frequency of any character in any substring in constant time. 2. Processing each query. For each query, left, right, k, the algorithm computes the frequency of each character in the substring s, left to right plus 1, by subtracting the prefix frequencies at right plus 1 and left. This gives the exact counts of each character in the substring. 3. Odd character count. A palindrome requires at most one character with an odd frequency. The algorithm counts the number of odd frequency characters in the substring, which is derived from the computed frequency differences. For check feasibility with k, each odd frequency character pair requires one modification to form a palindrome. Thus, the number of modifications required is odd_count //2. If this value is less than or equal to k, the substring can be turned into a palindrome with at most k modifications. 5. Result storage. The result for each query is appended to the result list, which is returned at the end. This approach pre-processes the string in O(n) time and handles each query in O(26) constant time, making it highly efficient for multiple queries on the same string. Here, we start by defining a method called canMakePolyQueries, which takes a string s and a 2D array queries as input. The goal is to determine if certain substrings of s can be rearranged into palindromes by making at most k changes. To do this efficiently, we use a prefix frequency array called prefix frequency, where each row corresponds to a prefix of the string and each column tracks the cumulative frequency of a specific character from a to z. Initially, we populate this array by iterating through the string. For each character in S, we copy the frequency counts from the previous row and increment the count for the current character. This pre-processing step ensures we can quickly calculate the frequency of any character in any substring of S. Once this is set up, we create a list called result to store the Boolean answers for each query. For each query, we extract the left and right indices of the substring, as well as the maximum allowed modifications, k. Using the prefix frequency array, we calculate the frequency of each character in the specified substring and initialize a variable called oddCount to track how many characters have an odd frequency. If a character's frequency is odd, we increment the oddCount variable. This count is important because, in a valid palindrome, at most one character can have an odd frequency. For all other characters, their frequencies must be even. Once we have the total count of odd frequencies, we check if the number of modifications allowed, k, is sufficient to make the substring a palindrome. Specifically, we divide oddCount by 2, because each modification can adjust one mismatched pair of characters, and compare this value to k. If oddCount/2 is less than or equal to k, we add true to the result list, indicating that the substring can be rearranged into a palindrome. Otherwise, we add false. Finally, we return the result list, which contains the answers to all the queries. In this problem, the task is to check if specific substrings of a string can be rearranged into a palindrome with at most a given number of changes. A palindrome is a sequence that reads the same forward and backward. To solve this efficiently, we use a prefix frequency array. This array helps us quickly calculate the frequency of each character in any substring by pre-computing the cumulative counts of all characters from the start of the string. For instance, with a string like ABCDA, this array will enable us to instantly determine how many times each character appears in any given range without repeatedly iterating over the substring. This pre-processing step is critical for handling multiple queries efficiently. Let's break it down further using an example input, the string ABCDA and the queries 0, 4, 1, 0, 3, 0, 1, 2, 0. The first step is to build this prefix frequency array by iterating through each character and updating the cumulative counts for all letters from A to Z. Starting with the string ABCDA, we initialize the prefix frequency array with all zeros. As we process each character, we increment the count for the corresponding letter. For the first character A, the count for A becomes 1, giving us 1, 0, 0, 0, 0. For the second character B, the count for B increases to 1, resulting in 1, 1, 0, 0, 0. Continuing this process for C, D, and the final A, we update the array to reflect the cumulative counts, 2, 1, 1, 1, 0. This array now allows us to calculate the frequency of each character in any substring efficiently. To process a query like left, right, k, we determine the frequency of each character within the substring by subtracting the prefix counts, prefix_frequency, right +1, j, prefix_frequency, left, j. This difference gives the exact count of the jth letter in the substring being queried. Now, let's evaluate the queries. The first query, 0, 4, 1, asks whether the substring ABCDA can be rearranged into a palindrome with at most one change. Using the prefix frequency array, we compute the character frequencies as 2, 1, 1, 1, 0. Here, A appears twice, and B, C, and D appear once each. A palindrome can have at most one character with an odd frequency, so we count the odd frequencies. B, C, and D give us an odd underscore count of 3. To make this a palindrome, at least odd underscore count //2 is equal to 1 change is needed, which matches the allowed k equals 1. Thus, the result is true. The second query, 0, 3, 0, checks the substring ABCD with k equals 0. The frequencies are 1, 1, 1, 1, 0, all odd, leading to an odd underscore count of 4. This requires odd underscore count //2 is equal to 2 changes, exceeding the allowed k equals 0, so the result is false. The third query, 1, 2, 0, evaluates BC with frequencies 0, 1, 1, 0, 0, resulting in an odd underscore count of 2. With k equals 0, no changes are allowed, making this false as well. After processing all the queries from the first example, we arrive at the final output, true, false, false. This output corresponds to our results for the 3 queries. The first substring can be rearranged into a palindrome with one modification. but the second and third substrings cannot meet the palindrome condition within their respective constraints. Now, let's look at another example to reinforce the approach. Consider the string app and the queries 0, 4, 1, 1, 3, 1, 0, 1, 0. As before, we first construct the prefix frequency array. Starting with all zeros, we update the counts as we process each character. After processing a, B, and C, the array becomes 2, 2, 1, 0, 0 by the end. This array will now help us efficiently evaluate the queries. For the first query, 0, 4, 1, the substring app has frequencies 2, 2, 1, 0, 0. The only odd frequency is 4C, giving an odd underscore count of 1. With k equals 1, the condition is satisfied, so the result is true. The second query, 1, 3, 1, evaluates AB. The frequencies are 1, 2, 0, 0, 0, with an odd underscore count of 1 due to a. Since k equals 1, this is also true. Finally, the third query, 0, 1, 0, checks AA with frequencies 2, 0, 0, 0, 0. There are no odd frequencies, so odd underscore count is 0, and with k equals 0, this is true. The final output for this example is true, 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 showing that all three substrings meet their respective conditions for forming palindromes. When analyzing the time complexity of our solution, we can break it down into two main steps. First, we pre-compute the prefix frequency array. This involves calculating the frequency of each character from A to Z for all prefixes of the string. Since the string has a length of n, we iterate over it once, and for each character, we update a 2D list of size, n plus 1, x26. Each update consists of copying the previous frequency array, which takes constant time with respect to the alphabet size, and modifying one value. Therefore, the time complexity of this step is O(n) multiplied by the constant 26, which simplifies to O(n). Next, we process the queries. For each query, we determine the character frequencies for the specified substring using the prefix frequency array. This is efficient because it only involves subtracting two arrays of size 26, which takes constant time. Additionally, we count odd frequencies and check whether the allowed number of modifications is sufficient, both of which are also constant time operations. With q queries in total, the time complexity for this step is O(q) multiplied by the constant O(1), which simplifies to O(q). By combining the time complexities of the two steps, we find that the total time complexity of the solution is O(n) for the prefix computation and O(q) for query processing, resulting in O(n plus q). Now, looking at the space complexity, the largest contributor is the prefix frequency array. This array has dimensions n plus 1, x26, which means it requires O26n space, or simply O(n). For query processing, we use a temporary list to store the frequency differences, which is of size 26, adding O(1) space. Finally, we store the results of all q queries in a list, requiring O(q) space. Summing these contributions, the total space complexity is O(n) for the prefix array, O(1) for temporary storage, and O(q) for the result array, giving us an overall space complexity of O(n plus q). To better understand the efficiency of our optimized solution, it's helpful to compare it with a naive approach. In the naive method, we would extract each substring for every query and count character frequencies directly. For a query involving a substring of length m, this would take O(m) time. If we consider q queries, the total time complexity becomes O, sum of lengths of all substrings. In the worst case, where all queries cover large substrings, this is O(q*n). The space complexity would also be higher since storing each substring requires O(m) space per query, leading to an overall space usage of O max substring length. In contrast, our optimized solution avoids these inefficiencies by pre-computing the prefix frequencies. This reduces the query processing time to O(1) per query, resulting in a total time complexity of O(n plus q). The space usage is also more efficient, requiring only O(n plus q) in total without storing any substrings. To validate the time complexity mathematically, consider the two main steps. During pre-computation, iterating through the string takes O(n) time, and updating the prefix frequencies involves 26 operations per character, leading to a total of O26n, which simplifies to O(n). For query processing, each query involves constant time operations, so for Q queries, the total complexity is O, Q. Adding these together confirms the overall time complexity of O, N plus Q. Now, let's analyze different scenarios. In the best case, with minimal values of N and Q, such as N equals 1 and Q equals 1, both time and space complexities are O, 1. In the average case, typical values of N and Q scale linearly, resulting in O, N plus Q, for both time and space. Even in the worst case, with large values such as N equals 10⁻5 and Q equals 10⁻4, our solution still maintains O, N plus Q, efficiency. This demonstrates that the optimized approach is highly scalable. By leveraging the prefix frequency array, we achieve a balance between pre-processing and query handling, making the solution efficient for input sizes of all scales. When tackling this problem, it's important to be aware of common mistakes that can trip you up. First, failing to handle edge cases is a frequent issue. For example, scenarios like empty strings, single character strings, or queries where k equals 0 often require special handling. Overlooking these can lead to runtime errors or incorrect results in corner cases. Another pitfall is inefficient substring extraction. If you repeatedly extract substrings within a loop, you can end up with an O, N squared, time complexity, which becomes a bottleneck for large inputs. Instead, techniques like sliding windows can help optimize this. A third mistake involves misinterpreting what at most k replacements means. Some confuse it with exactly k replacements, which leads to flawed logic and failed test cases. Lastly, ignoring the inherent symmetry of palindromes can cause redundant computations. Remember, a palindrome symmetry means you only need to check half the substring, which can significantly reduce unnecessary comparisons and improve performance. Now, another common variation involves overlooking constraints in the problem statement. For instance, failing to account for the maximum string length or the range of k can result in solutions that don't scale well. A solution might work fine for small test cases, but excessive time or memory usage will cause it to fail on larger inputs. To succeed, you need to keep efficiency in mind. In an interview setting, start with a brute force solution to clarify the problem, but quickly pivot to more optimized methods like sliding windows or pre-computations. Pre-computing mismatches for all substrings, for example, allows you to answer queries in constant time. It's also essential to clearly explain the trade-offs between approaches, whether you're prioritizing time complexity, space complexity, or both. Additionally, communicate any assumptions about the problem upfront, such as constraints on k or the input format, to avoid missteps. Finally, always test edge cases like empty strings, maximum length strings, and k equals 0 to ensure your solution is robust. This problem is closely related to several other LeetCode challenges, which can provide additional practice and insights. For example, LeetCode 5 focuses on finding the longest palindromic substring, while LeetCode 5.16 deals with the longest palindromic subsequence. LeetCode 6.47 asks you to count all palindromic substrings, and LeetCode 13.12 requires determining the minimum number of insertions to make a string a palindrome. Exploring these problems can help you recognize patterns and develop a deeper understanding of palindrome-related techniques. As for alternative approaches, one option is the sliding window method, where you maintain a fixed substring and calculate mismatches on the fly. This eliminates the need for repeated substring extraction, optimizing performance. However, it does require additional bookkeeping. Another approach is to pre-compute mismatches for all substrings. While this allows you to answer queries in constant time, it's more memory intensive and involves a higher pre-processing cost, so you need to weigh these trade-offs carefully. Dynamic programming offers another robust approach. By using a DP table, you can track mismatches for substrings of increasing lengths, systematically solving the problem for all possible queries. While this method is space-intensive, it provides a structured way to address the problem comprehensively. Alternatively, the two-pointer technique is a simpler, more space-efficient option. Here, you compare characters from both ends of the substring and count mismatches as you go. The downside is that without pre-computations, you'll need to recalculate results for each query, which can add overhead. Each of these methods has its own strengths and weaknesses, so understanding the trade-offs will help you choose the right approach based on the specific constraints and requirements of the problem you're solving. Great job! To recap, we explored strategies to solve problem number 1177 efficiently and discussed how to optimize substring analysis. Remember, mastering these techniques will serve you well in both interviews and real-world coding challenges. Don't forget to like, subscribe, and stay tuned for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!